with you, you should have your notes as well as SLS easy for you to toggle back and forth. So let's look at the various parts of your SLS as well as your notes, and we know how to orient ourselves. Yeah. If you look at your SLS, they're organized into various folders, various tabs. If you look carefully, they correspond to the sections inside your textbook. So for example, let's look at your textbook. You should find 2.1, 2.2, right? What are the parts of the endocrine system? If you go into your notes, that's what you should see too. So if you go into your SOS, that's what you should see too. At the start of every folder, you will see the sections that we're going to introduce you to. Each section, 1, 2, corresponds to one of your sections in the textbook. Alright, so that's how you can relate back and forth. I'd like you to pay attention to how we've organized these set of notes because they will largely repeat themselves in organization for the subsequent chapters. This year, as you noticed by now, we've sort of graduated from all the small things, biomolecule cells. We're starting to go bigger, all the bodily systems, and I find that's the areas that biology students enjoy the most. So, you'll find that for a good 2/3 of this year, we're going to learn about systems in our body. We start off first with the endocrine system. After the endocrine system, we will go into the respiratory system, how you breathe. After that, we will go into the renal system, how you produce urine. After that, we'll go to reproductive system, how you produce babies. Yeah? So, systems, and very broadly, you'll find that we organize our learning this way. We'll always start off with some introduction of the topic, why we are studying this system. After that, we will go into the parts of the system. Unless you know the various parts, various organs, you won't quite appreciate how they work together. That's the next part. So how do they work together to achieve a particular function? Last but not least, we'll look at disruptions. How to spell disruption? What happens if one of those parts fail? How will it affect your entire system? Very broadly, all these chapters will go through this same format. Why is this useful to you? So that when you craft notes, broadly you can categorize information this way, regardless of which system you are studying. Always there will be, you'll start with parts, you learn about how they work together, and you will learn about the systems. If you encounter a question, it tends to also go in kind of this format. There will usually be a question on the structure, what are the various parts, followed by how do they work together, and then we'll usually end off with what happens if we disrupt one of the parts. Okay, so if you pay very close attention, the questions tend to follow this format also. So today, our focus is on the endocrine system, which just came from homeostasis. And we'll start off with the introduction, as well as the various parts of the endocrine system. Okay, sometimes I create tasks for myself that are too easy to complete so that I make myself feel accomplished. Okay, you open your SLS already, right? And then you downloaded the notes. Okay, very good. You only have 2 more things to do. Okay, so we'll start with the introduction today. Introduction to the endocrine system. But before I do so, I'd just like to do a recap of the previous topic, homeostasis. We just came from homeostasis. The idea of homeostasis is that we want to stay the same. Homeo means same, stasis means stationary. Our body is always trying to maintain that state, where our conditions within us are rather constant. Near constant within a narrow range, but never quite a flat line. So, why study the endocrine system? Let's do a quick recap of what we need to achieve homeostasis. Number one, we need some sort of a receptor, right? To be able to detect any change. Okay, so there's a change. Number two, we need a control center to interpret the change, to decide what to do next. Finally, a you always have an effector. The role of the effector is to counteract the change. If the change is to counteract whatever happened originally, we say that this is a negative feedback system. It is a negative feedback system because the change that the effector is bringing about counteracts what was originally happening. Okay? Negative in that sense. Not quite the negative feedback that your friends or teachers may give you in your life. So, why learn about the endocrine system? Because the endocrine system's role is in these arrows. Somehow, the receptor must be able to communicate information to the control center. The control center must communicate information therefore to the effector. Right? Why? Because the receptor, control center, effector may not be close to each other in your body. Give an example. The temperature receptors in your skin may be able to detect temperature changes, but the control center is all the way in the brain. The effector is back at the skin. So somehow there must be communication from one area to the other. This is just one example. So for the next two chapters, endocrine system and nervous system, the main reason why we're studying this is so that we can find out how our body communicates between the parts. So I'd like to emphasize that these way arrows I've drawn, it could be nervous in nature, or it could be endocrine system in nature. But I'm going to write down hormones because that's what really we are transporting around. Hormones. You know of some hormones in your life: estrogen, testosterone, adrenaline. These are all hormones. So why are we learning about the endocrine system? So that we can fill in this gap. Okay, so today's focus, we're going to do an introduction. I think we will reach the point of what hormones are, right? And after we're done with this chapter, we'll move on to the nervous system. I have to say that the endocrine system is a little bit dry. I have nothing to bring to class. Hormones don't look that amazing. They are kind of colorless in nature. No organs I can really bring either. But once we hit the nervous system, this year, it's been many years since we've ordered eyeballs. Okay, it's been ordered and it should come somewhere at the end of this term. Okay, and that is our favorite organ in the nervous system that we'll study. Not the brain. The brain is a bit too complicated. Scientists don't quite understand it fully either. And if you chop into it, it actually just looks like a squiggly soft mass. I've seen a real brain before, and actually the texture, if you cut into it, is kind of like butter. Like, not like really melted butter, but like butter that you just took out the fridge, then it rests a while, so it has like custard-like feeling into it. Okay, but we're also going to study the brain also because if you handle it, actually the brain comes with a lot of diseases that if get into your system and go straight to your brain, and your brain will become diseased. Yeah, so there's, and then also, I think that's one of the reasons why Singapore bans the eating of brain, because not quite safe unless you cook it well. Yeah. So, brains. Okay, so today we're going to start with the endocrine system and introduction. For this first part of the lesson, I'm going to be playing an introduction video up to a certain point only, very short. But I'll just like you, as you are listening, pay attention and choose some options from question 1. Right? After you listen to this video, can you identify the components of the endocrine system? Right? We'll take that as an introduction to this chapter. Okay, you can read the question, look at the options. If you're ready, we're going to begin. Okay, we're going to begin now.
In this video, we're going to discuss the endocrine system, which allows different parts of our body to communicate with each other. You might notice this is basically the same job as the nervous system, which it kind of is, but there are lots of differences between the two, and we'll explore these as we go through the video. The endocrine system consists of a series of glands that are found throughout the body. What they have in common is that they all secrete hormones, which are small chemical molecules that are passed into the blood and then spread throughout the body in the bloodstream. This allows the hormones to come into contact with a wide range of tissues. Some of these tissues, and it's important that it's only some of these tissues, not all of them, will have receptors that are specific to the hormones. And so the hormone molecules can act as signals to trigger certain changes inside the cells. We'll see some of these glands in more detail in other videos, but for now, let's look at the main glands in the system and see briefly what they do. First, we have the pituitary gland, which is sometimes called the master gland. It produces multiple different hormones, some of which directly tell the body what to do, and some which tell other glands to release their own hormones. It's not actually part of the brain, but it's pretty close, and it is attached to the brain. And on our neck, we have the thyroid gland, which produces the hormone thyroxine. This regulates the rate of our metabolism, and also plays an important role in growth and development.
Okay, we'll just pause here now.
Now, do you remember how earlier we said that
We'll
the
pause
pituitary
right now.
gland?
What are the parts of the endocrine system that you took note of? Okay. Maybe just want you to wake up. Okay, so the question is very easy. Yeah? Alright, so it says hormones. Right? If we need a means for communicating between the parts, the endocrine system's role is to provide that messenger. And that messenger is in the form of hormones. Okay. Anything else that is required in the endocrine system? Glands. Yeah? Hormones don't spawn out of nothing. They are actually secreted by organs in the body. And they are secreted by glands called endocrine glands, which gives rise to the name of the system, endocrine glands. Okay? Endocrine glands are responsible for producing hormones. They serve as these chemical messengers. So this endocrine system is rather special. If you look at our digestive system, you find that your stomach, intestines, duodenum, rectum, everything is connected to each other. Circulatory system, the heart, the blood vessels, all connected to each other. Respiratory system, the lungs, the windpipe, everything connected to each other. Endocrine system, however, is the system where the parts don't connect with each other. You can have one endocrine gland here, another one down here, another one down there, but they're not physically connected. What function do they serve? Right? If the circulatory system's function is to allow for transportation around the body, respiratory for you to breathe, renal system for you to produce urine. And what in the world is the endocrine system's role? It is to serve as a communication system using hormones. What it communicates, it really depends on what condition we are trying to regulate. That means to say, actually, we have many different types of hormones. There are many types of hormones present in your body. We also have many endocrine glands within your body, each one producing their own hormones. And so we don't go away thinking that we only have one kind of hormone in our body or one endocrine gland. We have many, each one producing their own. It is at this point that I'd just like to say that, at least based on what I've seen so far in what you're going to study, and also a lot of case studies online, usually from the receptor, the control center, I notice that they tend to use nerve impulses. Not so much hormones. Have, but not as many as you will see with nerve impulses. Okay? I say this up front because the case studies that you will be learning, you will see nerve impulse more so than hormones. Okay? Between the receptor to the control center. For example, you've already learned one. Thermoregulation. Thermoregulation, meaning regulation of your body temperature. Between the temperature receptors in the brain actually employs nerve impulses, not hormones. And nerve impulses are really, really fast. They are like electrical signals. And rightfully so. Actually, to be able to detect the change, you usually want to detect the change fast. And so it tends to be nerve impulse in nature, so they can detect it fast. The response after can either be slower or faster, depending on the nature of the condition. So you tend to find hormones being used between the control center and the effector. You will also find nerve impulses being used, but it really depends on what condition you're regulating. So let's link back to your previous chapter. In thermoregulation, between the receptor to the control center, actually we use nerve impulses. Between the control center to the effector, you know what messenger is being used? Okay, if you go to your notes, actually the messenger that is being used is also nerve impulses. Okay, not hormones. So actually, to regulate your body's temperature, hormones are not really used for this main pathway. We primarily use nerve impulses, and it's really fast response. Okay? Because temperature out of its range, right, can cause very bad damage to a lot of organs in your body. You need to react fast. So if someone were to ask you to describe thermoregulation as an example of homeostasis, you want to be careful because the means of communication is actually nervous system in nature. Okay, so you just be careful about that. Don't worry, with every homeostatic control that we need to perform, I'll let you know what is the in-between. Okay, whether it's nerve or whether it's hormone in nature. Okay? Okay, so if the body is sending out signals, we must have a way of receiving the signal. Right? Just like someone were to send a snail mail to you, you need an inbox or mailbox to be able to receive the mail, to know that you've got the message. Our cells have the same thing. And the effectors, you will find that there are cells. And on these cells, you'll find receptors. The role of receptors is really like a mailbox, to allow the hormones to bind to, and once bound, will send a signal to the cell that, hey, I need to do something, and that something could range from a lot of things. It could be that I need to maybe release some sugars into the bloodstream. Maybe I need to take in some sugars because there's too much sugar in your bloodstream. A wide range of different outcomes. Okay, so as an introduction, in the endocrine system, just three main things you need to know about. Number one, we have glands that produce hormones And the hormones are detected by receptors found on the effectors. Okay? Think of receptors really as a mailbox for the hormones.
What do you say the receptors are found on the effectors?
The receptors are found on the, okay, so I'll be very specific, found on the cell membrane of the cells of effectors. When we use the word effectors, usually they refer to rather big things like organs. Okay? Organs are made out of cells, right? So effectors have receptors to help to detect the message. Yes?
Wait, so is this like an example of homeostasis? Because if it is, right, that is no control center.
Which is an example of homeostasis?
Like, whatever you're talking about, like the hormones and everything.
Okay, the endocrine system is not an example of homeostasis. Homeostasis is the process where we maintain a near constant internal environment using three parts: receptors, control centers, and effectors. Right? So what is the endocrine system? Endocrine system is not equals to homeostasis. Endocrine system is the communication system that allows homeostasis to take place.
But if the receptors are found on the effectors, then
Okay. So this is where there's a slight confusion. Because in biology, they use receptors in many ways. So if you are very keen and you pay very close attention, actually we use it twice so far. We've used the word receptors once in the chapter of homeostasis. We've used now receptors again at the effector stage. Right? In homeostasis, you say we need receptors to detect a change. Now I'm saying you also need receptors on the cells of the effectors to detect hormones. Right? Okay. I'd like to say that we are using these words receptors the same with we use the same word because the intention and function of it is the same. In this case, we are detecting a change. This receptor is detecting hormones. Our body has many kinds of receptors. Some to detect this, some to detect that, some to detect hormones, some to detect temperature change, some to detect sugar level change, right? And so when I use receptors in this chapter, I mainly am focusing on the receptors at the end of homeostasis, the ones that detect hormones. Yes?
And where are those the first receptors found?
Oh, where are they found? Good question. They are found where the body condition needs to be closely monitored. So for example, if your skin surface is where temperature change is most likely going to happen, it makes more sense that I have the temperature receptors here. If I need the temperature of my organs to be rather constant, it makes sense that I have some temperature receptors there also. Let's say I want to regulate your blood sugar levels. It makes sense that I have receptors where blood is flowing through. Okay? So just three broad parts. 1, 2, 3. And I think I included in the SLS that what Jiaqi was just raised. There is this slight confusion that often arises with that word receptor. Okay, thanks for bringing it up. When I was a student, I got epically confused with homeostasis and endocrine system because of that one word. Didn't quite know where it was used. Then lied with confusion. So where can you find endocrine glands? There's one gland that's pretty huge that I think you can touch. Not directly, but it's just underneath your skin. Thyroid gland. Okay, so you feel for your Adam's apple. Yeah. Some have it more pronounced than others. Below your Adam's apple, surrounding it, this space over here, there's actually one huge gland, the thyroid gland. People who have disorders at the thyroid gland, sometimes you may see this area swell up a little bit. The thyroid gland produces growth hormones, so it affects your growth. So you don't go and choke someone in this area, because when you directly choke like that, you're actually like whacking their endocrine gland right there. Okay? You should be able to feel it's kind of squishy in nature. Okay? That's the thyroid gland. So if this is your neck, this is your Adam's apple, thyroid gland is actually really huge. Something like that. Where are your other glands? We have one gland in our brain, the pituitary gland. You often find pituitary gland, spelled like that, pituitary gland. You often find this gland drawn in this odd shape, like an inverted heart. It is located somewhere in the brain. This gland, you can pay close attention to. We'll visit it again and again in this chapter and the subsequent chapter. Do you have other endocrine glands? You do. Above your kidneys, there's this gland called the adrenal gland. This gland produces adrenaline. It's what hypes you up. It is also what makes you feel stressed. Right before an exam, you could be feeling rather anxious. You feel your heart palpitate. You sweat a little bit more. You breathe a little bit faster. That's all because of the adrenal gland producing this hormone called adrenaline. Actually, why in the world are we breathing faster, heart beating faster, sweating more? There's actually no point in it, right? If you're going to take an exam, how is that going to help you? In reality, it's not going to help you. This is a response that makes more sense if you are being chased by tigers or a mad clown with a knife. Yeah? In those situations, then you need some adrenaline to get your heart pumping, to make you breathe faster, so you're ready to fight, ready to run. But in this modern day, a lot of things we tend to now associate with life and death situations. Now we're starting to associate it with things that are not really life and death, like when we take our exams, or maybe right before a performance. To us now, modern day, when we remove all these tigers that can hunt us down, we associate things that are stressful to different things now, right? And it's not really good for the body, because in reality, if we cannot differentiate what's life and death, we end up getting our adrenal gland to produce adrenaline constantly, and it actually wears your body out. Your heart is constantly beating fast, you're constantly breathing fast. It is as though you have this much life, you end up working your body extra hard for nothing. Last time it made sense. If you're being chased by a tiger, you better start pumping your heart faster and breathing faster so you can run away. If not, you get eaten and your life gets shortened. But now we shorten our lives by wrongly associating things that are not life and death with life and death. So this is something that we need to learn how to control. In the next chapter on the nervous system, I will share a little bit about how we can take back some control. If not, you'll be too stressed. Other endocrine glands, let me think. Okay, there's one more big gland that we will be learning about, but I'll not talk about it yet. Let's talk about other glands in the body. Actually, one thing common about all your endocrine glands is that they produce hormones. We actually have other glands in our body that produce other things. For example, we have other glands that produce things like saliva, enzymes, mucus, tears, sweat. These glands can be found all over your body too. If you want to, you can feel the opening of your salivary glands. Okay? This one, don't reach your finger into your mouth. Just use your own tongue and you'll be able to feel it. So you try. Right now, underneath your tongue, okay, supposing you open up your mouth. Underneath your tongue, you should be able to feel two dots, two opening underneath. That's where, right, the saliva kind of squirts out from. I realized it one day when I didn't eat the whole day. Then I went to the canteen, right? Then I see the auntie, right, selling like fried chicken, right? Then I felt two squirts come from underneath. Yeah, so underneath your tongue, you go and feel there are two little dots. Can you feel? Can, right? Okay, it doesn't quite feel like dots per se. you can sort of feel like it's kind of raised, you know, like 2 points coming out. Yeah? Okay, don't believe, right? You don't believe? You just think of your favorite food right now. You can feel the saliva starts coming out from there.
They say you put it at the roof of your mouth, you can feel it pop out.
Big what pop out?
You can feel like someone control the saliva.
Oh, okay, I've never tried it before. Next time you see your favorite food, bring your tongue to the top, then you aim it at someone you don't like. Like a viper. And this is very interesting. These are openings. It means they are holes. What are these holes connected to? They're actually connected to tubes called ducts. Sorry if I didn't pronounce it well, not ducts. Okay, ducts. Ducts. These are little tubes that connect to the gland. So you have salivary glands. They are connected by ducts, and these ducts are usually connected to an opening directly to the target site. So you have salivary glands, you have tear glands. So over here you have some tear glands. You look in the mirror, you also see 2 holes. That's where the tears will come out from. On your skin, there are also a lot of pores. That's where the sweat glands, pores are, and that's where the sweat will come out from. So you notice all these substances are produced directly to the target site. Hormones are a little bit different. They're not produced to the target site. Why am I introducing this to you? Because you need to differentiate between the kinds of glands you have in your body. You have endocrine glands whose sole purpose are to produce hormones. At the same time, you have exocrine glands. And as the name suggests, exocrine means to the outside of your body. Exocrine glands. They produce substances directly to the target site, and it's not produced into your body or into your blood. It's produced on body surfaces. So it could be squirt into your intestines, squirt into your mouth, squirt out from your eyes, squirt out from your skin. Yeah. Endocrine glands, as the name suggests, endo means inside. It is secreting hormones inside into your body, specifically where? Actually into your bloodstream. Okay, I'll pause right now for you to just jot down anything you find valuable or extra. Okay, sorry, these are not extra, anything valuable to you. Yes, Ishan? Yeah. Oh, okay. Thermoreceptors. Okay, so you should ask, the thermoreceptors found on each skin cell. Okay, this is where I did not go in depth into. There are so many kinds of receptors. At this stage, when we talk about receptors, there are receptors that are found on cells, or it could refer to nerve cells that as a whole act as a receptor also. So it could be nerve cells, or it could be receptors on cells. Yes?
So endocrine glands like only produce one hormone each, or can endocrine glands like produce more than one?
Okay, good question. So we have many endocrine glands. Do they each just produce one kind of hormone? Some do, some don't. At least for the examples you'll be learning, they can produce more than one kind of hormone. Okay? So endocrine glands need not just produce one type of hormone, they can produce many types of hormones. Sometimes, if I'm not wrong, even though it produces many types of hormones, the hormones still serve the same, serve to regulate the same condition. So the example we'll be learning in this chapter, the endocrine gland produces 2 types of hormones, but both hormones serve to regulate the same condition, just in a different way. Yes?
Is it like, the effectors, right? The receptors to bind the hormone. Is
Yeah.
there only one hormone to a receptor? Or like, can you bind to multiple things at once?
Oh, okay.
Multiple things happening at once? Or
Okay.
only like one?
Okay, so are you asking, can a hormone bind to multiple receptors or just one?
Like, can the receptor bind to multiple
So maybe I have 3 types of hormones. Can they all bind to a single receptor? No, they function a little bit like enzyme active sites. It needs to be complementary. So what this means is that this particular hormone may be of a slightly different shape. This particular hormone may be of a slightly different shape. And in order for a particular cell to be considered the effector, it needs to have the correct receptor to detect the message.
So one receptor only has one specific hormone.
Correct, yeah. So like an active site. Yes. Why do we need so many glands? Because we have many conditions we need to regulate. Say again. Oh, why not have just one central gland that produce all the necessary hormones required? Is it? Good question. I don't know. Maybe it's by evolution. It could be that we actually had just one central one, but as we evolved, as a species we evolve over time, it could be that new needs arise, and then new organs, new glands arise from it. Yeah, I'm not too sure why. It could also be, if all the conditions are important, right? You only have one central gland, right? You knock out that one gland, you have one, right? Yeah, could be that purpose, that reason. Yes, Mani. Okay, so if I was not clear, actually we have many different cells in our body, maybe at different parts of the body too. Maybe this cell is at the brain, maybe this cell is at your stomach, maybe this cell is at your skin, maybe this cell is at your foot. Each cell could have their own receptors. And hormones could be flowing everywhere at any point in time. But if the hormone is not able to bind, then it will not trigger the cell to carry out its effect. Right? So that means to say, if we have this red hormone passing by the skin, right? After all, our circulatory system goes to every part of our body, right? So if this red hormone comes by the skin, it's fine. It's not going to activate the skin to do anything. If it goes by the foot, it's not going to activate the foot cells to do anything. But if it goes by the stomach cells and it binds to it, then it will activate the stomach cells to do whatever effect was it required it to do. So it has that specificity to it, the hormones. Yes?
Then can one receptor cell have can one effector cell have more than one receptor?
Can. So I like that you all just keep probing more and more. So whatever I teach you is just the bare minimum. Whatever we are going into, it is FYI, but it gives me some ideas when I'm going to craft your quizzes. Okay, so can it have more than one receptors? Can. So it could be that the skin cell has this particular receptor and maybe this particular receptor. If the purple hormone binds to the receptor, it will cause the skin cell to do a particular effect. If another hormone that binds to this complementary this receptor binds, it will trigger the cell to carry out another effect. So one cell will carry out different effects, but it depends on what message it receives. Yes, Mia?
Are there like competitive inhibitors that might block the receptors?
Wow. That's a great question. By virtue of the fact that they work by complementary nature, right, I would assume that there could be inhibitors. But to my knowledge of studying biology, I don't think I've read up about it. Yeah. But it makes sense to have inhibitors. It makes sense to have inhibitors. I think you are likely right that there are ones. I think when we hit the reproductive system, we will learn that some hormones are able to inhibit organs. I imagine that when they inhibit the mechanism, I have not looked into it. Perhaps it's through this competitive nature. Yeah. Anything else? Okay, so why don't we just ask, thank you, you're pushing it forward a little bit deeper. Okay, so that is the broad concept of the endocrine system. So that is an introduction. Then what is the rest of the chapter for? Right? It kind of feels like we're done. Okay, so the rest of the chapter is really about what are the parts. We're going to look at the endocrine glands a little bit more in depth. Okay? We're going to look at hormones a little bit more in depth. I say it's a chemical messenger, but actually, what biomolecule is it made up of? Right? Everything I talk about, I'd like you all always to question back to JH3. Actually, what is it made up of? Right? When I say that this is a receptor, is this receptor cellular in nature? Is it made up of protein? Is it made up of lipids? Right? Okay, so there's an introduction. Now let's test ourselves. This video you've seen many times, okay, on regulating blood osmolarity, right? I would like you to rewatch this video again. I would like you to tell me, okay, so you have two blanks below. I'd like you to decide. Let's watch this video again. I'd like you to decide. Do you think that this particular condition, blood osmolarity, is it regulated using nervous system as a means of communication? Or is it regulated using endocrine system as a means of regulation? This is the skill to pick up, right? I may give you a paragraph to read. You pick up and sieve out the information to deduce which system we are using to communicate between the parts. Okay, so let's have a look at this video. You watch this video many times.
Imagine you're lost at sea and really dehydrated. Water levels in the blood decreases, and this makes the blood more concentrated and solutes. In other words, the osmolarity of your blood increases. This is detected by receptors in the hypothalamus. These receptors are called osmoreceptors. When the osmoreceptors detect an increase in blood osmolarity, it sends more nerve signals to the pituitary gland. This results in more antidiuretic hormone to be secreted into the blood. The secreted antidiuretic hormone then travels to the kidneys where the nephrons are. Nephrons in the kidney filter waste products, salts, and water out of the blood. The last part of the nephron, called the collecting duct, is where water reabsorption is regulated.
Now I want you to pay attention to the cells of the collecting duct. You will find now with this new lens after what we just learned, there are actually receptors on the collecting duct, okay, to detect the hormone.
Antidiuretic hormone receptors are located on the walls of the collecting duct. When antidiuretic hormone binds to the receptors, it causes a cascade of reactions in the cells. Vesicles containing aquaporins, which are membrane protein channels that allow osmosis to occur, will be inserted into the walls of the collecting duct. More water can now be reabsorbed from the filtrate into the blood at the collecting duct. And as a result, the filtrate and eventually the urine becomes more concentrated and lesser in volume. In addition, because there is now more water in your bloodstream, blood osmolarity decreases back to its normal range. Unfortunately, we're still stuck at sea.
Okay, may I get you now to type in your responses in there, and then we will look at everyone's thoughts. Do you think it's regulated in the nervous system or the endocrine system?
Okay, let's watch the video again.
share your thoughts. Which one do you think we are employing? Some of you type very fast. How can I tell the time? Okay, let's have a look at some of your friends' responses. So, are we using the nervous system or the endocrine system to regulate blood osmolarity? Okay, that is what you were seeing, blood osmolarity. Okay, layman's term, right? Actually, we are looking at salt concentration. So, what are we using? Okay, let's look at some of our friends' responses. Nicole says that nerve signals are used, so likely it's the nervous system we are using. Sion says nerve impulses are used also. When you send nerve impulses are sent to the pituitary glands in the brain, so it must be nerve impulses. It must be the nervous system being used. Okay. Valentina says blood osmolarity has to be rectified quickly, so that's why we should use the nervous system because it's quite fast. Okay, so we see different approaches here. One, Nicole and Sion, they think nervous system is being used because of what they observe. They observe that nerve impulses are found in this homeostatic control. For Valentina, she's thinking more of the nature of what needs to be regulated. If I need to regulate this fast, perhaps I need to use the nervous system. Okay, and we look at other responses, quite similar in nature. Kylie also brings up the nerve impulses being brought up. Santosh also talks about the nerve impulses. So it must be the nervous system being used as a control, the communication means. Shanice also mentions nerve signals. Tanya also approached things from kind of Valentina's point that blood osmolarity is something you regulate and rectify quite quickly. And she also mentioned rectify quickly, therefore, perhaps the nervous system needs to be used. She also mentioned that thermoreceptors are also used, and these thermoreceptors will send some nerve impulses. Okay. Mia also approached the thing quite similarly to Valentina and Kanyu. Okay. Zoe approached it from the perspective of she observed nerve signals are being used. Okay. Yihui mentioned nerve impulses too, so did Keller. Okay, and if we scroll down, I think largely we kind of approach it from the same point of view, right? Okay, I think if you look at this system, one challenge I face is I don't know who the control center is. Can you tell? Okay. I have trouble identifying. Okay, we can tell what the receptor is, right? The receptor, as the video said, is not thermoreceptor, osmoreceptor. But what about the control center? What is the control center? Is it the pituitary gland? I think I mentioned this last time, I cannot remember in this class. But I think when I read online sources, people don't quite pinpoint and identify who exactly is the control center. So if you really need a control center, I think just broadening it a little bit as the brain is still quite safe. Yeah? But if you look at this particular system, it's a bit weird. The osmoreceptor is also situated in the brain. So actually these 2 points are very close to each other in location. Unlike what we've learned in thermoreceptors, where it can be very far apart. Your skin thermoreceptors to the brain is very far apart. But actually the osmoreceptor and the control center, they are almost right beside each other, which makes it difficult for us to tell who is the control center. Okay, so I'd like to say, number one, you're right. Actually the nervous system is being used to a certain extent for this particular homeostatic control. What about the endocrine system? Is it being used in this particular homeostatic control? Okay, Tanya wrote quite a lot. She said that Actually, since blood is found across the body, and when we talk about blood osmolarity, actually impacts almost every part of your body. So it will make sense that we need to use the endocrine system, where hormones flow through the entire circulatory system, every part of your body, because it affects every part of your body. Kaisin also mentioned that actually the pituitary gland will secrete antidiuretic hormone, right? You heard the word hormone. So it must be some sort of endocrine system being used. Valentina brought up hormones too, and in Viscona, I think many of us brought up hormones as the means of communication. Now, I'd like to see through to see if we have anything different. Okay, I think Xiaqi then mentioned that at the end of it all, there's a receptor to detect the hormone. Okay, so this is very hallmark of the endocrine system. We have receptors to detect the hormones. And many of our friends' responses also kind of hit the same idea. The idea that they notice that there are hormones and there are also receptors found on the particular effector cells. So, which system are we employing? Are we using nervous system or the endocrine system? Both. Okay. Why am I bringing this example up? Because it's a very beautiful example where we crisscross both communication systems. Both nerve impulses and hormones are being used in this particular scenario. Good news is that in your JH4 life, you will actually be learning 3 main homeostatic control systems. You've already learned temperature, right? How we regulate temperature. You will learn about how to regulate blood osmolarity 2 chapters down the road. But I mean, you watch this same video many times. By the time we hit that chapter, you already know it. The last thing we are going to learn how to regulate is blood sugar level. Just 3 homeostatic systems. Why am I writing this now? Because I want you to take note of which communication system we use for each condition. For temperature, we use the nervous system primarily. For blood osmolarity, as you have just discussed as a class, we use both the nervous system plus the endocrine system. Blood sugar level, when we come to it, then you interpret yourself also. Okay, which system we are using. Yes, Zoe.
Do we need to know like in depth how the blood osmolarity process goes? Like we need to know the Exocrine and all that.
Yes, but not now. So, 2 chapters down the road, you will learn all of this, and actually, it will be easier then. Okay, now there are too many terms being introduced that don't quite make sense, like collecting duct, nephron, kidney. But once we've dissected the kidney, all of this will become second nature to you. Okay, one thing I really like about our class is that we brought out one interesting thing. I think Hanyu and Valentina kind of touched on this. The idea of actually what are the pros and cons of using nerve impulses versus hormones? When might you want to use either? If both serve the same purpose to communicate, right? Then why not just use one of them all the time? Why do we have two different means of communication. Are there pros and cons? Yeah? I'd like you to think about that. May I get you to buzz with your neighbor? What do you think? What are the pros and cons of using the nervous or system or hormones? When might you want to use either or? Okay, then we see how much we can get from our class. Okay, what do you think? What are the pros and cons of using either or? When might we want to use either or? And as you just found in this particular example, we use both, right? So, I'd like to say that this question popped to my mind. Try to find answers online. Many different responses. So, I would say there are many right answers here. What do you think? Rick, what do you think? Okay, nerve impulses are faster than hormones. It is true. Nerve impulses are electrical signals. They travel through cells. Okay, we have specialized cells called nerve cells, which you will learn in the next chapter. These nerve cells, right, they're specialized because they are very long. Unlike a lot of cells in your body, they are just small and cute, right? Nerve cells are elongated in nature, and they can transmit electrical impulses from one place to another. So you have some nerve cells, they are very long, they can reach from your brain down to your arm. Yeah, and they carry nerve impulses quick and fast. Hormones. To get a hormone from one place to another doesn't travel by cells. It travels via your blood vessels. Travels via your blood vessels to various parts of the body, right? So it takes a while. It needs your heart to pump, then it can reach the relevant parts. So Rain's point, speed. That's one consideration, speed. How fast do we need this information to get to where it needs to get? Any other differences in these two means of communication? And how it might play into when you might want to use either? Yes? Okay, you can. Okay, that's a very interesting thing. Nerve impulses and hormones. Actually, hormones, right, are something that you can externally ingest. Yeah, actually, it's true. Ishan is right. You could take some hormones orally. Sometimes it could be injected straight into your bloodstream. Nerve impulses travel via nerve cells. I would assume the best closest thing to eating a hormone is that you electrically charge someone, right? But as Mia was pointing out, that could kill a person. It's a execution method.
Then don't the AEDs that like give you outside, don't those use electrical?
Right. So there are some there are some medical equipment. They use these electrical impulses to detect what's happening in the body. Nowadays we have electrodes. Or actually, then let's go example. We do use electrodes nowadays to modulate the nerve impulses traveling through the body. Some people, for example, Parkinson's patients, if you've seen a person with Parkinson's, their brain has degenerated to the point where you see their hands tremble. The trembling is a result of the nerve impulses being transmitted not at a regular rate. But with electrodes that can pulse nerve impulses at a rather regular rate, it can give the person back that control. Okay, that's an interesting thing, that actually you could modulate the both communication means. Yes?
But actually, because like, wouldn't it be easier for us to like target certain changes in the body using hormones? Because we don't really understand nerve impulses completely yet. So like, it's very hard to like make it do one specific thing.
I think it also depends on what you want to control. Some things, right, you can only control using hormones, some using nerve impulses. So I think it also depends on the nature of the effect. Anything else that we might want to consider with regards to these things? Other than speed as a factor. Yeah, Nicole. Okay, maybe about the length, duration. How long term is the effect? I think Nicole is right. When it comes to duration of the effect, it would seem that nerve impulses, the effect it triggers tends to be quite instant and short term. The effect of hormones tends to last quite long. But I would caution to say that we put this as a definite thing, because it's hard to also tell, the impact of a nerve impulse. Sometimes the impact of a nerve impulse is to trigger a gland to produce a hormone. So then the effect of it is also quite long in that regard, right? Okay, but broadly speaking, it would seem to be the case. The impact of hormones can be quite long term. Any others? Oh, okay. That's interesting. The level of control. I guess so, right? Voluntarily, you can control your body parts, at least those connected to a skeleton, and those are using nerve impulses. But actually, I cannot think of an instance where I can control myself to produce a hormone. So, actually, hormone secretion is all involuntary. You cannot voluntarily do it. But nerve impulses, you can do some voluntarily, some involuntarily. That's interesting. Any other differences that you might? Yeah?
How like widespread it is.
Okay, perhaps how the spread. How widespread it is. You notice, hormones travel via the circulatory system. So it could technically impact wherever the circulatory system reaches out into, right? Nerve impulses, however, it is a single cell with a very long body, and so it's kind of point to point. It travels from one point to another. Unless you have many cells reaching out to every part of your body, then the impact is kind of far-reaching in that sense. But hormones, travels through the blood vessels, can reach a lot of parts of the body. So I like what Toy brought up earlier. She said actually to regulate blood osmolarity, or blood sugar levels even, actually if you think about it, this condition is present throughout the body. So actually it makes a little bit more sense to use hormones in this instance. To control myself using the markers right here, it's very specific. I only really want to control this part. No need for hormones. It also gives me the speed, right, to move my hand like that. You will not encounter a question where we give you a choice. Should I use nervous or should I use endocrine? because whatever is in our body has already evolved to be as such. It may not be the best, but we've evolved to employ either or, depending on the condition. But we will not give you an imaginary one for you to choose. Okay, this is just a thought exercise for us to think a little bit about why there might be two different means of communication. Yeah. Oh, okay. Are there examples, case studies, where both are applied at the same time? Not that I'm aware of. Based on the case studies we're going to study and the ones I'm aware of, we use either or. Okay? For example, even in the example of blood osmolarity, right? It was nerve impulse first, then hormones. Right? Thermoregulation is nerve impulse and nerve impulse. I don't quite know of an example where they use both. Yeah? Okay, so this is, I would say this is extra, but I think it gives a little bit more value in why we have two different systems. There's one thing that I find very important about nervous system that our hormones just cannot do. Whatever you're doing now, right? From your blinking to fiddling a pen in your thumbs, that's not something you can control using hormones. It will take too long, right? So the beauty of nervous system, not only is it used in homeostasis, it's also used for you to control your body in various ways. Okay, so that is one part. The last part of today's lesson, we're going to have a look at this particular organ here. We're going to apply whatever we've learned so far. We've learned about the differences between an endocrine gland and an exocrine gland. One of them produces hormones directly in the bloodstream. Exocrine glands make use of ducts and then they secrete it to the target site. I'd like you to look at this particular organ, the pancreas. Will you share with us your thoughts in the space below? Do you think the pancreas is an endocrine gland or is it an exocrine gland? You need to be sharp. Look at the information provided to you in this image. And there are clues embedded in it. Endocrine or exocrine gland? What are the clues?
It's actually quite easy.
For those that would like a little help, at time point 3:13 in the video above, they actually summarize everything very nicely. Some classes they will screenshot this and then they park it inside their notes also. Right? Differences between endocrine and exocrine glands. Okay, these are the differences. I'd like you to ignore line number 2. Bio teachers, we have no idea what they're saying. Okay, ignore number 2. Look at 1, 3, 4, and 5. These are the ones we were talking about earlier. Based on 1, 3, 4, and 5, you think the pancreas is an endocrine or exocrine gland? This is at time point 313. If you'd like to screenshot this, paste it somewhere, go ahead. gland is this. This is the skilled pickup. Based on the differences we know about, then the skilled pickup here is to be able to identify if something is an endocrine or exocrine gland. Okay, we'll gradually move into your friends sharing. Okay, let's look at Keller's point. Boom. He observes that there are ducts and there are also hormones being secreted. Two hallmarks of an endocrine and exocrine gland. Endocrine gland, exocrine glands always have ducts, endocrine produce hormones. How do you say that it's likely part of the endocrine system?
What?
It also has a duct, it's likely part of the exocrine system because it has a duct directly connected where the digestive enzymes can directly go to the duodenum, which is the target site. However, also endocrine because it produces hormones and it goes to the bloodstream without ducts. Let's relate back to the previous JH3 topic. If it doesn't make use of ducts to get into the bloodstream, then what transport process might it use? How might a hormone go from the endocrine gland into the bloodstream? Okay, so actually a mixture of transport processes. You try to pay attention. Sometimes it may be using vesicular transport, like exocytosis. Sometimes it may be using simple diffusion. It boils down to something we learned in JH3. What is the hormone made up of? If it's too big, cannot use diffusion. If it's small enough, it uses diffusion. If it's hydrophobic, can pass through cell membrane. If it's hydrophilic, cannot pass through cell membrane. So it's all JH3 knowledge being applied. Okay, so other than Han Yu, Shani says both. She thinks it's both because she saw that two hormones are being secreted, insulin and glucagon. So it must be some endocrine system. We also exocrine because we have enzymes. Enzymes are not hormones, so likely exocrine nature also. Yishuan says both for the same reasons that Shanice brought up. Jiaqi brought up the endocrine gland because he observes that two hormones are being secreted. Rin also brought up the it's likely an endocrine gland because of the hormones that regulate sugar levels. Okay, Christine believes it's both for the same reasons that we saw above. And then we look at the rest are largely the same also. Okay, Valentina says secreted into the intestines, and she considers that body surface. It is. So although the intestines are inside your body, it is still on the surface of your body, not into your bloodstream. Okay, so that's what the nature of exocrine. Okay, Igor also thinks it's both. Okay, I'll let you take note. Bile. Okay, I know this is a long time ago, you learned it in JH2 2 years ago. Bile is produced not by the pancreas, but it's produced by the liver. Yeah? And then it is stored in the gallbladder, which is then released from there. We'll not test you this, we'll not test you JH2 stuff. Okay? Zoe thinks it's exocrine because she noticed that there are enzymes being secreted and it's used outside, yeah, on the body surface. Yuan also exocrine because of the enzymes, endocrine because of the hormones, and Isabel also thinks it's both for the same reasons. So which is it? It is both, but it's more exocrine than it is endocrine. If you look at the pancreas, the parts that produce the parts that produce exocrine, the parts that produce enzymes, actually there are more cells that produce exocrine enzymes compared to the endocrine cells. For your level, saying both is good enough. Okay? So you may be wondering, how is it possible a gland can do both, produce exocrine enzymes as well as produce hormones? It's because this particular organ comprises different kinds of cells. Some cells, like the alpha and beta cells, produce hormones. And then there are some cells called the acinar cells that produce enzymes. So, as we all know, organs can be made up of different types of cells. But you were sharp in identifying Therefore, it to be exocrine, you need to have a duct. Here's a duct. And it produces into a body, onto the body surface. And then there's the exocrine gland nature, endocrine gland parts because of all these alpha beta cells. You also observe that there are blood capillaries, right? And it goes directly into the bloodstream. Okay? Here, the enzymes go directly to the target site where it is going to be used, the enzyme, to digest food. I love this example because again, it breaks the generalizations that we learn in biology. We always teach you the general models, but the case studies prove us otherwise. And here's a good case study of a combination of both. So if we were to ask you to write an essay or a story about a gland, and they ask you for exocrine gland, feel free to use this as an example. If they ask you for an endocrine gland, also okay to use this because it is both. Okay? We have around 8 more minutes today. Tomorrow we will, is it meaningful to speed rush? Okay, tomorrow we will go into the types of hormones. We know about what produces hormones. Then let's go into what are hormones made up of. Okay, and I think the question that should come to your mind is actually what biomolecule is made up of. May I get you to go to practice makes progress? Shall we do some questions? Practice on the spot. Very simple check.
Oh, right.
Thank you.
So,
Yes, you should. Initial input output is very low. It's your question, why are you using nervous system? Because of what you observe.
that's this produce
It's both.
No, it's not.
So we don't classify homeostasis in the any of our systems. We say that we need to use these two systems to be able to achieve homeostasis for cells. Yeah, correct. In order to achieve homeostatic control of that condition. Okay, so these two systems, right, are not equal to homeostasis. It is required for homeostasis. Okay, I hope it's quite doable. Okay, I don't think I will really need to go through this, but anything that struck you? No, after yes. Yeah. Oh, okay. So what do you put? You put true. You put false. bind permanently to these receptors. They can detach. Yeah?
When they detach,
Yeah, when they detach, yeah. So something that is irreversible would be, right, if the binding is permanent. But the binding of hormones is not permanent. Okay, it binds, it can later on be destroyed by something else to remove the effect, or it could detach to remove the effect.
how does it like detach? Is it like
How does it detach?
why?
Why would it detach? I think it would detach because unlike an enzyme reaction, where it binds to the active site, then some reactions can occur, right? There's no reaction here. It is really I touch there, temporary bonds, and it detach as much as it could easily attach. So it is as readily than it detachment. I'm not sure. I think the cell will control it if it directly destroys it, but I'm not sure if it can control the detachment process. But I would think that it can detach by itself because the bond shouldn't be strong. Okay, I think that will be all for today. Any questions you have for these two questions? Not tomorrow we'll complete folder A. Oh, okay. What's what, yeah? So what's part of the endocrine system? I cannot remember the answer. Okay, adrenal gland, yeah, that's one of the examples. The liver. I cannot remember a hormone we produce there. Okay, thanks for shaking your head. Okay, so no one. Lungs, not that I'm aware of, that it produces hormones. Ovaries, I think it does because it has estrogen, that's where it comes from. Pancreas, we know that it is a combination of both. Pituitary gland, yeah. Salivary glands, no. Okay, because I can squirt out my saliva. Okay, testes, yeah, because it produces testosterone. Okay, so at least for this example, I think of the hormone that it produces, then I can identify what it's called. Okay, that is all for today. I'll see you again tomorrow and we'll continue on. What's up? What's up? Right, you all must do your